Welcome, everybody. Tonight we're going to be focusing on Unit 5, and we are going to be talking about the Unit 5 content, which is NLP Data Preprocessing Part 1. You can see the list of topics here on the screen. I will pull the PowerPoint up here in just a moment, and we'll start going through the material. And I'm going to stay in non-screen present mode if you guys don't mind. And let's get rolling, right? So just a quick recap of the topics from last week. We talked about data visualization again, and you see that over and over again, and why we use visualizations to represent data. We also looked at N-grams, named entity recognition, topic modeling, and text complexity as topics. Now, this week it says we're going to look at more classification techniques and kind of dig into it a little bit deeper. And the ones that we're going to focus on predominantly are the ones called bag of words, the TF-IDF, and the word to vector models. We're going to look at how to convert documents to vectors and how to perform comparison of documents. And then it says hands-on training of machine learning models to classify documents. So we'll see how that goes, right? And you can tell by my reluctance here, there's some of the hands-on stuff that we've been handed by Intel seemingly has become deprecated very quickly. So I always get a little bit pensive about using some of it verbatim. So we'll see through our experience. All right, let's get into the topic here. So we're going to talk about classification. This is not a new topic for us, right? So when we did machine learning, we talked about this stuff pretty extensively, and how we can classify certain things. It's basically a way of organizing information, classifications. So classification algorithms then identify the class to which an instance belongs. And now that you guys are programmers, right, we use this word instance, which means one, like rubber stamped version of an object, right? Like we instantiate stuff, right? So one instance. And in this case, they have the example of the cat, and we look at it and we're classifying it. We go, that's a cat. We can tell just by looking. All right. So classification, though, is basically not necessarily an automatic, right? Like computers don't learn like humans do, but we can train computer models to identify and classify things. And, okay, with an image, right, we can see a cat and go, yeah, that's a cat. Look, it's got whiskers and pointy ears and it's really cute and fluffy, right? But we're talking about classifying words, right? So we're looking at the features of words and forming a classification. And notice that text features are classified as n-grams, right? So this is kind of a synonymous term. And then we try to figure out, based upon the words in a document, what kind of document it is. Is it, for example, is it fiction? Is it a news story? Is it something else? We can classify it. So the point is that we can take information, look at it on the inbound, and then try to figure out whether it's about a certain topic or not. For example, if I pulled in a document and it said Green Bay Packers and tie score and Dallas Cowboys and poor clock management and oh my God, we almost lost, that kind of thing, you would know right away it's about sports, right? Right. And if I was talking about AI and LM Studio and NLP and Python and oh my God, the file is blank, all that stuff, you would know you were talking about the Unit 4 homework in my NLP class, right? And I think this is kind of interesting, right? Because think about it, when you look at a document or you read an article, that's kind of what you do, right? I also find it really interesting too, like if you use like an aggregated news service like I do, like I don't like go to one news site ever. Well, that's not true. I go to a couple of news sites and I read the content, but mostly what I do is I use news aggregators that give me headlines of things I'm interested in based upon the articles I've looked at previously with them. So if I'm on like the Google News feed and I'm always looking at AI articles or get articles about electric guitar, it's going to give me a lot of articles related to that, right? And what it's really doing is it's taking the content of those articles, looking at it, classifying, goes, oh, he's always like looking at documents that talk about X, Green Bay Packers, for example. So there's some classification going on there, so it's basically identifying the content. We did talk about algorithms as it says here, but here we're going to look at these particular ones, and we mentioned this as we were getting rolling. I like the term bag of words. That one's kind of clever. Notice the acronym for it: the TF-IDF, which is term frequency inverse document frequency. Yeah, that's a mouthful. That's why we just use the acronym. And then the word to vector approach. We'll start by looking at the bag of words. All right. And let's look at this concept here. It says text data is messy. And indeed it is, right? It says machine learning algorithms prefer well-defined fixed length inputs and outputs. So they don't really, those models don't really want like a bunch of superfluous language or information, right? And it also says that those algorithms don't work with raw text directly. They must be converted into numbers first. And this is really kind of a weird concept. Wait a second. I'm going to take a word that has meaning, and then I'm going to turn it into a number, and then analyze it and try to figure out what it means. It almost doesn't seem intuitive, but when you think about the fact that machine learning algorithms are all mathematical formulas, right? Then it starts to make sense as to why. So they use this word again, vectors. And remember, a vector is kind of like what you're seeing on the chart here. It's basically a line with an origin point and a value or a strength and a direction, right? So mathematically, that's what a vector is, like an arrow line pointing in a certain direction. And here they're taking some words and like king, queen, man, woman. Notice how king and queen are longer vectors because they're probably more important than just man and woman, right? Do you see like kind of the point there? And the fact of like vectorizing something is to convert it into some sort of a mathematical representation. So the vectors are derived from the actual text, right? So we look at the text to convert it to a vector. We call that feature extraction. These are terms we've used before. And when we use bag of words, it's just it is a pretty simplistic method of actually doing that, and allows us to basically get that classification piece laid on top of it. So for example, they have a little snippet of text here. This is a sentence, right? And I don't see a period at the end, but I do know that it is a sentence because it has all the aspects of a sentence, correct? It has more than one word, and it's a phrase that makes sense together. And if I did put a period at the end, it is a complete phrase. There's a verb and a noun and a subject and all that kind of stuff. So because a sentence can be broken down into pieces, we can then start to analyze it. So it says here that bag of words is a representation of input text that points out the occurrence of words within a document. So for example, notice how, they're pulling a little snippet clearly from like Genesis in the Bible, right? And they're analyzing the words there, and they find the word beginning, and that happens once. And then we find earth. Well, that happens twice. And then we talk about God, that happens 3 times. So out of all those words, which one's probably the most important? You can argue it all you want. But in terms of just the occurrence in the text, right? If I'm like, for example, if I'm writing about the Green Bay Packers, I might say Packers this, Packers that, Packers this, Packers that, football this, Cowboys that, but mostly I'm saying Packers, right? And so that has more weight to it. It says any information about the order or structure of words in the document is not retained. So we don't care which word came first. We only look at the words that happen in the document and really how many times they happen. So it's like, let's take all the words, we'll throw them in one container, and then we'll analyze them that way. We're not looking at their order, what sequence they came in, or anything like that. Move on. So here's how the process goes with bag of words. First, we have to get the data. The data is the words itself. And it says, assume that we already have it, right? So here's the first sentence. Welcome to the NLP course. Sentence 2, NLP course teaches you to process text. All right, so we got 2 sentences there. All right, so it says the vocabulary consists of all the unique words in the 2 sentences. So I take all the words out and put them into one. Notice it's a Python list, right? Square brackets and comma separated. We got welcome to the NLP course teaches you process text. Now, granted, how did they put them into that structure? Well, the order in which they came in the sentences. But after a while, you can imagine if I had sentence 3, 4, 5, and 25 or whatever, that would, the jumble of words would become more jumbled, right? Even though some of the order is preserved. But based on those 2 sentences, we have a vocabulary length of 9. So we have 9 unique words inside there. Right. So the goal then is to turn it into vectors. And then since we have 9 of them, each one will have its own vector that forms around it. It says for each word in the vocabulary, put 0 if the word does not appear in a sentence. If a word appears in a sentence, we put the number of times it appears. Now, we already talked about that. So like in the little example snippet from the Bible, right? God appeared more times than earth or beginning, right? And so we're just counting at this point. So if we started to create a vector for the first sentence, it would look something like this. And notice we're forming a little table, we're labeling it, we're taking each word, making a column header out of it, and then we're tabulating the total. Now, in the bag of words, we have all the words from the other sentences too. Those clearly haven't been processed yet, but the first sentence has, and these are the vector values basically at this point. So we count all those, and then notice what happens to the vector definition. Given all the words in the bag of words, we are incrementing the count for each word relative to the first sentence. So the first sentence has a vector of what you see here. It's 1, 1, 1, 1, 1, 1, right? 0, 0, 0, 0. Right? And I'm not sure if I said that the right number of times, but that's how you convert it for the first sentence relative to the bag of words, right? And remember, it's relative to the entire complexity of the word. So if I had a document with 1,000 sentences, right, you can imagine there would be a lot more words in the bag of words, and the vectors would get much longer, clearly. And notice it says here, these words occur once in sentence 1 with the value 1 in their position, teaches you to process text. Those don't occur in sentence 1, so we put 0 in their position. Okay, I think that's pretty intuitive. So sentence 2 rolls around, right? And it says NLP course teaches you to process text. And now we're scoring that. And notice how the vector for that one looks a little bit different, right? Because now we're tabulating the count just for that sentence with those particular words, and the words that don't appear, which are welcome and the, those get zeros. All right, so here's kind of the activities that they're pointing to. And I don't mean to belittle what you guys are capable of, because normally I would say, like, you know, given a longer session, I would totally want to walk through these and do them. But as I alluded to, like, basically the homework assignment is kind of related to this, so I don't want to kind of spoil that in the process. But if you follow the techniques that we just looked at on the slides, this is pretty easy. So your bag of words would basically contain what? I am there, we are not there, where is everyone? Right? All of that is the bag of words. Then you go sentence by sentence and create a vector. Now, I'm noticing that sentence 1 and 2 have words that repeat. You know, and how do you handle that? That's, I guess, the first question. And then there's also this one. And notice this also has a lot of repeating words. So it was the times of, right? And then you get kind of like through a process of it and really discover that there's far fewer unique words than you might think. And I think this is really kind of the goal here is, are those unique words ultimately more important than the ones that are constantly repeating? No, that's arguable, right? Because if I was writing an article, let's say about the Packers, I might say Packers a whole bunch of time, but I would argue that's very important. Here it says it was the of, that happens a lot, but is that really important? Okay. And this is now if you're kind of trying to wrap your head around that, you'll see what I'm talking about in terms of, the importance of it. There's also this one, right? So they have 3 activities, and this is not a bad one to practice with. And this can be, and I'm just going to put it out there, like the precursor to your assignment to do that. So if we wanted to implement this in Python, right, assuming it works, right? So I feel like I have to like throw in that little caveat now, like a little asterisk. Let's talk about the libraries first. So we're, scikit-learn is on the table once again, right? We've talked about this, so I'm not going to really hammer it too hard. We've also used pandas many times over, right? And you notice how like we often use the same libraries because these are the ones that do the work, folks, for a lot of these things. So those two are, so scikit and pandas are important ones here. All right. So they give a little bit of an example of the coding, right? So if we were to do bag of words, we need 2 libraries. And then from scikit-learn, they have a vectorizer tool or function built in. So that's kind of the one that we're focusing on. And if you guys remember with pandas, this one we use for like really generic data manipulation, and it builds data structures for us and data frames and things of that nature. All right. So that's the import statement. Then we build, notice, a corpus, right? And that's an arbitrary name. It could be named anything, but that's not an uncommon term to use here. And we can take the text from an entire document and then in between quotes or double quotes, single or double quotes in a Python list structure, drop in all the information. Now you can imagine this could become quite large, right? Assuming that each one of these sentences, right, is considered a document in a sense. So basically it says this lists the sentences we want to turn into vectors. From there, we run it through the count vectorizer and run that function. And I want to kind of point out this Python technique here. This is really common technique. And Python programmers kind of do this quietly, by the way, when they're coding. And that is, they'll take a function that's pre-created, and in this case, count vectorizer is part of scikit-learn, right? And normally when you run a function, you call the function, drop your information or parameters inside of it and run it, or trigger one of its methods. But what they're doing here is they're taking that function and they're storing it in a variable. So whenever I want to use that function, I just use the word vectorizer instead. The parentheses are gone, notice, right? And this is like one of those things, like if you're taking that Python class with me right now, which is like intro level, and you'll kind of hear me saying some of this stuff, you can put anything in a Python variable. It's totally true, right? Any like weird structure. And a lot of times we do that just to simplify it. So it's easier to type vectorizer instead of count vectorizer parentheses. That's the point. And some might even take it farther and just call it like VEC or V or something like that. Once we have that, we still have all the methods and functions that are attached to this function. And so fit transform using dot notation in Python is a method inside of count vectorizer. So it's a code API that we can call by using that. And notice we can use a little bit simpler syntax as opposed to appending this to the end of that. Okay, it's not really much of a savings, but you can do that. So this would take the fit transform, right? And it takes the sentences set as the input, and the print statement prints the whole vocabulary. So this procedure here is, the fit transform, and then get feature names, and then basically it converts it into that bag of words. So now we have a bag of words. That's basically what that does. Now, we also can take these and convert them to vectors, and notice how the vectors turn out, and we have word counts here, which words are happening relative to the bag of words and how many times they're happening. And then once again, they look like Python lists inside of lists, but I don't see commas separating them right away. So it's just text output. All right, so the process then is collect and process the data as discussed in the previous session, right? So wherever it is, where are you getting your data from? Oh, I'm generating it, or I went and downloaded it from somewhere. It's in a JSON file or a CSV file, or maybe it's just a plain text file. I went to Kaggle, I went to this data website, and I pulled it down. Then we create a dictionary, which is a list of all the unique words in your data. We create the document vectors. So it says for one document, refer to the list of unique words and count the number of times each word appears. We're using like sentences at this point, but it could be entire documents. And then you repeat that process for every document for each one. I'm trying to point out here, this has limitations, right? Okay, so it says in the previous examples, we found vocabulary is a unique set of words. And it says naturally the bigger documents have more vocabulary, right? So it would make sense if I have a 10-page article that's going to have a lot more variance of words than a 1-page article, right? Absolutely. If the vocabulary gets really big, the vectors get really big too. So if I have like 10,000 unique words, well, my vectors are going to be, 10,000 characters, or 10,000 positions long. That's how it is. And no surprise, last bullet. When you have vectors that are that complicated, it's a lot more challenging to process because that's more information to process for the computer. And remember, we're taking the words, converting them to numbers, but the numbers still need to be processed. So how do you get past that? All right, so there's a few different situations that we can use. So one thing that you could do is you could ignore the case of a piece of text. So for example, if I use the word the at the beginning of a sentence and put a capital T in front of it, I can count that as the same word as one that's in the middle of a sentence and doesn't have the capital. And I think most people say, yeah, that's fine. Makes sense, right? You ignore all the punctuation. So like maybe a sentence that ends with the word finally and has a period after it, or one that ends with an exclamation, they shouldn't be treated as two different things. Let's just ignore the punctuation. That's irrelevant, right? Another thing, right? It is possible that your document contains misspelled words. Let's just look at the word achieve. Very common to superimpose the E and the I. All right. And so we can fix that and then count it as one word. And then it says ignoring stop words, right? So like words that would terminate a sentence, basically. We can also use stemming and lemmatization, right? Which we were just learning about in the previous units. And if you look at the little graphic there, right, we bring in raw text. So noisy entity removal, which is removing HTML tags, stop words, punctuation, white spaces, URLs, etc. So like on a web page, if you ever look at the code, right, it's like all this stuff that really isn't the content, even though that's what we're seeing on the screen. So when you're like processing a web page, you got to remove all that stuff before you get to the content. Text normalization, so we tokenize it, do the lemmatization, stemming, sentence segmentation, etc. And then word standardization, where we use regular expression and lookup tables. So these are all part of the process of cleaning up the text, right? And really what we're trying to do is just make it simpler to process ultimately. So that's the approach. Says here, another method could be creating a vocabulary of grouped words or creating n-grams. So for example, it was there, or there was something, are phrases, that we could group together and treat as one thing. So that is a possibility. Another example, Green Bay Packers. I could group that in because that truly is one singular concept, right? In fact, I could probably even group it with just Packers or just Green Bay if I'm talking about football. And this is kind of the combination approach. And right there, if I combine Green Bay Packers together, well, that's 3 less words to process, or two less words to process. Okay, so here's another activity here. It says generate the vocabulary of bigrams. Now, what are bigrams? 2-word combinations, right? So for example, NLP course maybe is taught in summer. You see, like, I think that's what they're alluding to here. And then they have ML course. Okay, and I would say is not taught. Maybe, as a combination, or taught often, or is not and taught often might be some of the bigrams that you have there. Another one here, if you want to keep practicing, right? And this would be trigrams, the groupings of 3 words. And here's the weird question, right? Like I used the Green Bay Packer example. That's a trigram for sure. Could we, and this is kind of like where my brain goes on it, so I'm just going to show you my thinking. Could I group like these 3 together, and then could I group those 3 together, and then could I maybe group, see where I'm going with that? Like I make different groupings within the group, and is that allowed? And is that maybe a logical way to proceed? Perhaps, so that's the kind of like when I'm going to trigger your brain to think about it there. All right. It says here, well, some words may occur more frequently in a document and dominate it, right? And it says these frequent words might not always convey as much informational content to the model as rarer words that might give more information on the domain of the document. And this is what I was kind of referring to before, right? Just because I say the word a lot doesn't necessarily mean it's important. Maybe it's the words I use more seldomly that are actually more important, or like if it's a bigram or a trigram or whatever. And this is why they call it n-grams, because we don't know how many words together that really represents. For example, if I had a n-gram of blocked field goal, right, that might be more important than me saying Green Bay Packers 500 times in the document. All right, let's move on to the next one here. And we are going to take a break in a little bit, but I want to get some more content flowing here before we do. All right, so now we're looking at the TF-IDF approach. And it says, unlike the bag of words, it focuses more on the words that convey context, right? This is usually a better option in machine learning models, which is kind of an interesting thing. And there's this graphic here, and what I'm going to attempt to do with the graphic so it's a little easier to read is I'm just going to make it just a little bit larger. And it says it's a measure of originality of a word by comparing the number of times a word appears to be in a document with the number of docs and the word appears in. Right? So, and they have a mathematical formula for this. Of course they do, right? Now think about this. Because we are doing machine learning models over the top of it to do the processing, we have to convert it to math, right? And they first focus on how many times the term appears in a document. So this really defines, right? The TF is the term frequency. So the term is the T and the document is the D. How many times does that term appear in that document? And then they go to the inverse document frequency, which is the converse. So the frequency of the term relative to the document. So in other words, in how many of the, and I'm not saying that well, in how many of the documents that we're looking at does that term appear? So if I read articles about the Green Bay football game this past weekend, and I'm sure if I read ones from Texas, they would read a lot differently than the ones from Wisconsin, right? And how many times might they say, I don't know, poor clock management, or blocked field goal, or Jordan Love, or whatever, right? You guys feel where I'm going with that. So that's a different measure. So how many times, or excuse me, how many documents does that term appear in? Is kind of my point there. All right, let's take a break right now, because now it's going to get a little deeper here. Let's take a 5-minute break. We'll pause for a few minutes. It's 8 or 6:30. We'll come back at 6:35. So I'm going to pause and we'll resume in a few minutes. All right, welcome back from the break. We're now going to press forward and kind of reinforce this term, this TF-IDF approach. And once again, right, this is a combination of two different approaches kind of meshed into one, right? And I want to make sure that you guys understand that. So term frequency, really, if you think back to bag of words, it's very similar, right? Because we're looking at the words and how many times they appear in the document. We're counting, right? And then we do this inverse thing, which is how many times that term appears in different documents, right? So, and then we use that as kind of like a countermeasure to kind of balance out the values so we can train our models. All right. Now, maybe this isn't what we want, though, and I'll have you think about this. It says raw term frequency is not something we want. Right. So it says a document with 10 occurrences of the term is more relevant than a document with 1 occurrence of the term, but not 10 times more relevant. Right. So you can imagine if I was reading the Green Bay newspaper about the Green Bay game, they might say Green Bay Packers like 50 times. Right. And then if I read the Dallas newspaper, they might mention the Packers once. They might just go the other team, the opponent, that kind of thing. It doesn't make the phrase Green Bay Packers less relevant, though. That's kind of my point. We're still talking about the same thing. So relevance does not increase proportionally with how often a word happens, right? And I think that's pretty intuitive. Now, the IDF approach kind of does a different thing. It says the principle is basically that if the words are more rare in the document, they might be more informative than the words that are frequent. For example, as I'm talking, I'll use the word the over and over again. And it kind of really is superfluous completely. It has no meaning almost, right? It's just kind of like a part of speech. And of course, this is what we call a stop word, the, of, etc. Right? And you guys should know that already. And it says, consider a term in the query that is rare in the corpus. For example, if I had some sort of a question I typed into Google and it had a bunch of stop words in it, but then it noticed the word ornithology, well, that looks important, right? Even though it's just one of the 20 words in my query. So it says here that a document containing this term is likely to be relevant to the query, ornithology, and so we want to give that more value or give it a higher weight, right? And how do we do that? We do that numerically. And it says most often, words that are more frequent are less informative than rare terms. And I think I gave you like stop words are the great example on that. So document frequency, right? Or the inverse document frequency is the number of documents that contain the term. And we define IDF as the inverse document frequency. Now, without getting kind of into mathematics, right, too deeply, I can pose this question. And I know when you guys look at these formulas and you go, oh my God, I hate this math stuff. And then we have this logarithm here. What's a logarithm? Yeah, you can Google it if you want. But basically, it's kind of like um, the inverse of a power is a good way to look at it, right? So, like if I take any number x and I square it, I put a little two in the corner, or I cube it, or whatever the power happens to be. Um, a logarithm is the inverse of it. So, in other words, it's, and I'm looking at a definition here from Google, thank you. It says the logarithm is the exponent to which a given base number must be raised to produce a certain number. and and so if we do like a logarithm, for example, if I take the number 10 and square it, it equals 100, and the base 10 logarithm of 100 then becomes 2. You see what I mean? So if I take the logarithm of a number that's fully expressed, already been calculated, I can kind of say that that's kind of the same as 10 squared, right? So this is just basically taking the exponent and putting it in the root. Is kind of another way to look at it. And here they're defining n as the number of documents. So if you care mathematically about that, I'm going to say it's kind of irrelevant. I'm not really asking you to calculate it. However, here on the activity slides, they are asking you to calculate it, and I don't really want you to go to the trouble of kind of mechanically do it. But if you want, you do have the formula here, so you could take the numbers, you could type them into your scientific calculator or a spreadsheet for that matter, or if you're clever, you can write a Python program to do it. But I'm going to stop you right there because this is why we use Python libraries, so you don't have to write this stuff. Right? We're trying to understand the concepts. All right, so it is calculatable, and what they're doing here is they're saying these terms appear in these documents X number of times. So like here's the frequency in the document, and then we have to calculate the inverse of it. Now, ultimately, what we're kind of leading to is to do this comparison between words and how frequently they occur compared to words that are rare but may have more value. And there's kind of this slope that forms, and it is a curve. I want you to notice that because logarithms, when you plot them, do have curves on a graph. So stop words, they occur often, but have very little meaning, right? So they're at the far left side. There's lots of them, but they don't mean much. Then we have these rare words over here, ornithology or whatever, and those are important, but they're rare. And then there's words that are kind of in between, right? And it says the idea that words appear everywhere might not be as important as words that appear rarely. And that's kind of the reinforcement here. So here's kind of a way to look at it. Look at how often a word occurs, how many times that each word appears per document. That's kind of like bag of words, right? I mean, that's really the TF part of TF-IDF is really bag of words. I mean, we're not breaking it down the same way, but it really, that's what we're looking at. It's how many times does a word happen? Right. And it says TF-IDF weight is a product of the TF weight and its IDF weight. So we're multiplying those two calculations together. The TF weight increases with the number of occurrences within a document, but its increase is not proportional. Okay, and that's kind of what we're saying mathematically. But the IDF weight increases with the rarity of the term in the collection. And that's what the logarithm brings into the equation because we're flipping kind of the power upside down. So the rarity of it makes it more valuable. Right? And that's how we do it with math. So somebody had to like think all this through, right? And then what mathematical thing can we use to represent it? And that's what they came up with. So a quick summary of TF-IDF, right? Right. We combine those two weights. We consider all the words equally, compute the weights based on the frequency and the rarity combined. We want to identify rare words that are important. We also want to start ignoring all the weird stop words and things that just happen all the time. And the more of the rare words that we identify, the more important they become on that scale, right? And because we're doing a combination of those two approaches, this is pretty effective at really finding the important words in a document. Here's the steps to do this process, right? And we're going to walk through them now one by one. So here's the conglomerated version of it. We're going to go one by one on them. So let's just go through it. So step one, go through all the documents and count the number of documents where the word appears at least once. All right. So here we're counting the number of documents, right, where the word happens at least once. Here, if these are all documents, Andy appears in 2 documents. Step 2, write that number down. All right, I guess we did it. Step 3, repeat that with every word in the vocabulary. So after looking at all the words and all the documents, we go through and we start to score them, how many times or how many documents they're appearing in. And this is called the document frequency. For each number in that frequency, take its inverse, right? So it means dividing the total number of documents by the document frequency. So I have 3 documents and 2 occurrences, right? I take the occurrences and divide it into the number of documents, right? Rather than putting the 2 on top of the fraction, we're putting it on the bottom of the fraction, right? And then finally, they would say multiply each row in your bag of words by the log of the inverse document frequency. And oh my gosh, I do not want to do this math. You can make a spreadsheet do this math. But once again, we use Python libraries. The Python libraries handle this component. So these are the calculations that would go into each cell. And I want you to notice that they're doing this over and over again on a document by document basis. And then ultimately, if you calculate it through, you'll end up with a table of information, which is kind of like a list of vectors, right? That have numerical values to them. Then I want you to notice here which words have greater numerical value than others, right? And notice that like and, it's got a pretty high number on it, right? And then other words that are kind of generic are kind of weird, but notice like therapist, download, health, chatbot, example. I mean, and I guess that's pretty high. So maybe that word wasn't used a lot. But could we agree from looking at this information, maybe with the exception of and are, stressed, therapist, download, health, chatbot, that seems pretty, those seem more important, correct? I mean, I think so. You might counter that thought. All right, so they have a little challenge activity here, and if you really want to punish yourself, go ahead and try to calculate this, right? And once again, I'm not trying to steal away from the homework, and this is the kind of thing that they're signing in the homework, and I'm trying to like tweak it so it's more reasonable for us. So we'll see how that goes. All right, let's do a little comparison now between the bag of words and the TF-IDF. So the bag of word vectors are easy to interpret, but TF-IDF is generally better for machine learning models, right? So in other words, as human beings looking at the information, it's easier for us to look at the bag of word output. It says TF-IDF contains more information on the more important words, but bag of words create a set of vectors containing the counter words. Okay, we know that already. All right, now let's look at a different algorithm or approach here called word to vector. So the first two are pretty popular, but they do not consider context. Okay, so this is the important aspect here. By context, we mean the ability to detect the difference between an apple as a fruit and an apple as a company, right? So if I'm talking about my MacBook, I'm talking about Apple, the company. And if I'm talking about, Macintosh, I might be talking about a fruit. Okay, that's not a good example. But you guys feel where I'm going with that, right? Because that, like Apple Macintosh, that could go either way because we do have Macintosh apples. but maybe we have like, I don't know, a Honey Crisp. Okay, that sounds like a real apple. So the context is clearer. And this is where we use this technique from Word2Vec, which is called word embedding technique, which allows us to understand or help understand that context. All right, so Word2Vec basically says it's a popular method for representing text. It converts words into vectors, right? And then notice here they have man and woman. That's kind of a weird because one's singular, one's plural. I don't get it. And then it converts it to a numerical vector. And let me go back to this graphic that we looked on really early on. And I pointed out the fact that queen and king are longer vectors, maybe more important, Then we have generic man and woman. And I want you to notice they have like the example here. So king minus man plus woman equals queen. Okay. It makes no sense. I mean, from a logical standpoint, but basically what they're trying to point out says if you subtract the vector of the word man from king, add it to woman, you get the vector of the word queen. So in other words, these numerical representations play off of each other. They're interrelated. They're not standalone like counts of words. One affects the other. So here's an example. The kid says he likes playing cricket. The child says he likes playing cricket. So this Word2Vec algorithm would basically learn the embeddings from a large, data set. And basically the point is that it would figure out eventually that if I say kid and child, they're kind of the same thing. It starts to recognize based on large data examples, kid, child, come up with a different word for kid. You think of one? Infant, I don't know, whatever. You know where I'm going with that they're kind of interrelatable terms. So really the two sentences are kind of saying the same thing, aren't they? Yeah, they are. Right. So the other aspect of this is it looks at the relationships between those words and it preserves them in that context. And the bag of words and the TF-IDF do not do that at all. They don't care what order they're in or what the words mean, right? The other advantage is it deals with the addition of new words in the vocabulary. So if you give it new data, it builds its vocabulary, and ultimately it makes better results, especially in machine learning. And machine learning is how everything processes, folks. All right. So working with Python, we have this library called GenSim, right? And these are some of the tasks that it performs. Converts words to vectors, right? And that's the one that the algorithm we were just talking about. We can convert documents to vectors. It finds the similarity in text, and it also can summarize text. And they have a GitHub link here. I don't know if that's functional app. You can go explore that on your own. So here they have a little example of using it. And if you want, they have an example here where you can actually download the model directly if you want to tinker with it. But notice that they are doing an import of GenSim models from Word2Vec. That's the first line here in the fuchsia. And then they have the syntax for taking all of that information. And it's kind of an interesting data set there. It says Google News vectors -300. Doesn't sound like it sounds like all bad stories, basically. And they show you the parameters. So they have these vectors that have been generated. Bin typically implies binary information, so it's encoded in a binary, and you can see the binary true is on, and normalization is also on. All right, so it's loaded from the GenSim library, and then it converts the text to vectors, and basically it's a pre-trained Google News corpus. So in other words, they've already built this, and notice how many words are in that corpus. 3 billion running words. And the word vector model is 3,300,000 dimension English word vectors. So they're just telling you how much data is in there. So if you want to check out that model, I mean, I can just kind of click through to it here and take you there. And notice you can't preview it, so you can't see it on screen, so you have to download it. I'm just going to hit download. I'm just curious to see what the size of it is. Can't scan. Okay, fine. I want you, oh, it's 1.5 gigs zipped. It is in gzip format, and I don't know if you guys can see this well, but that file format, it's a binary file, but it's in gzip format, meaning you have to decompress it on a Linux machine. You can also decompress that on an Apple machine. There's ways to do it in Windows, but it's not pretty. But it's 1.5 gigabytes compressed, which maybe if you decompress it might be like 3, 4, 5 gigs just of text. That's how big this data set is. Absolutely huge. And I'm not going to go through that process right now because I value my disk space, basically. All right. It says to print a word vector, just do this, right? Getting word vectors of a word. And basically what you're doing is you're taking this word dog, right? And we are using it basically, it says as a parameter to create the vector for that word. All right, let's do a little comparison now. So word to vector kind of does this. So you got 2 sentences here. Obama speaks to the media in Illinois. The other sentence, the president greets the press in Chicago. This is kind of what I was talking about, you know, like what did the Dallas newspapers say about the game and what did the Green Bay papers say about the game? You can bet they're going to be different perspectives, right? Even in the words they use, even though in a sense, right, they're saying the same thing. It says these sentences have no words in common. They convey nearly the same information, a fact that cannot be represented by the bag of word model. Interesting. Because the bag of word model does what? It counts the frequency strictly of the words. The word to vec approach does this. You know, this is kind of how it works in the background. It goes, oh, Obama, you're talking about the president. Right? And today it might say Trump. Okay, whatever. Doesn't matter who the president is. And then the president speaks or greets. Okay, kind of in the same category. Then we're talking about Chicago or Illinois. Yeah, Chicago's in Illinois. And probably if president's visiting the state of Illinois, he's probably stopping in Chicago. Makes sense, right? And then media and press, once again, kind of the same context or meaning. So the word to vec identifies this, right? So it looks at one document, looks at another document, understands that there's a connection there between those. So next slide. It says here that the data pre-processing is essential for language or large language models actually perform accurately. And here are the key steps involved. Right, so let's take a look at those. First, we take our text and we clean it, right? Fix spelling, get rid of upper lower case, ignore the punctuation, etc. Normalize it, tokenize it, right? Split the words apart, and then start converting it into vectors. And then we have the data necessary to start building our large language model. And I think this is really fascinating. We have to go through all those steps. But now you guys are in the AI data analytics degree program, and you learn that aspect when you take a regular data analytics class too. Like somebody can hand you a spreadsheet of numbers or whatever, and sometimes there's information missing or corrupted or misspelled or misentered or what have you, right? And that process of either eliminating that, fixing it, adjusting it, whatever you have to do to make the data set workable, you do that. Here it goes a little bit further, right? So we're not only like doing those initial steps, we're cleaning it, we're making it more functional for us to process and eventually turning it into numbers. That's the vectorization, so that we can process it with models. Remember, machine learning processes math, not words. And I think that's really an interesting thing always when you think about it that way. All right. All right. Just to kind of reiterate these steps, and I've already been saying it all along, but reinforcement is not a bad thing. So cleaning the data involves removing noise and irrelevant information from the text. Okay. Spam data, raw HTML, offensive content, any duplicates of information, irrelevant, inconsistent data. So like if it's misspelled, incorrect spelling, whatever. Junk data, like gibberish, boilerplate stuff. So let's say you look at one article, and at the beginning of it, they say some stuff that they say in every article that's kind of irrelevant. We just get rid of that. If there's stuff missing, we try to see if we can fill it in or remove that portion of it. And then we look at stuff that are outliers. You know, it's like, why the hell are they talking about the Minnesota Vikings during a Packers Cowboy game? That kind of thing, right? Or it's not representative of the whole, and there's an indication of some sort of bias in the data, which of course we don't want, because we want to get good results. Normalization involves transforming the text into a standardized format, right? So, and mostly what this is, and I'm going to say most common, is to take uppercase things and turn them into lowercase, and or vice versa, right? And I think the general norm is to go lowercase. I'll have you compare that, and Python students, right, the ones that are currently, we're going to talk about this next week, but past Python students, like if you're asking somebody to type in a piece of information so that you can react to it, often you convert it to one case or the other. So if you're writing like an if statement around it, you don't have to say check capital A and lowercase a. You're only checking one, so you write less code. So it's more common, and it kind of like strips out that stuff. Now, interestingly, okay, getting the lowercase stuff out, okay, great, or making it all lowercase or all uppercase, I get that. But removing stop words of the and whatever, and although and might be more relevant than of or the, you could argue. Handling contractions, right? And this always makes me think of like Lieutenant Commander Data on Star Trek, because he could not do contractions. He had to say cannot, will not, shall not. You know, he couldn't do can't, won't, don't, or shoulda, woulda, coulda, probably, right? So that's kind of an interesting one, because those do mean the same thing. Or if we abbreviate Mr. And change it to Mr., you know, or vice versa. So those are normalization techniques. Tokenization, of course, is the process of splitting the text into individual words and or subwords, or in some cases characters. Right? It just depends on what your action is. If we're just looking at words and sentences, right, we're just going to break it down into words. But maybe if we're looking at subwords, you know, okay, maybe I'll go back to the Green Bay Packer example, because if I say Packers, Green Bay is implied. Or if I say Green Bay, Packers is implied. And maybe that's not even a good, because then we're looking at an n-gram. But maybe something to the effect of like, you know, necessary or unnecessary, where the un is a subword, you know, that negates necessary. That's maybe a better example. And in other cases, and we know we can do this in Python coding, where we can take words and break them into individual letters, right, for various purposes. It says this helps the model understand the language structure and enables further analysis. Absolutely. Then there's the vectorization. Of course, that's taking the text info, turning it into numerical data that we can process with our large language models. And it says common techniques include word embeddings, you know, word to vec and glove, and then and subword embeddings such as fast text. Right? We haven't really talked about those a lot, but that's stuff that's on the table. The other thing is, it says here, improving accuracy through data preprocessing. Our and we have these these breakdowns here. So like, and I'm going to start here at the bottom and go around where we're handling data imbalance, right? And actually they have a little breakdown here at the bottom of the screen, so you can just read that to go along with it. And they're starting with noise reduction. It says by removing irrelevant or noisy data such as characters, punctuation, HTML tags, right? We talked about all these. Standardization of data, standardizing the text by converting it into a consistent format, lowercase, contractions, abbreviations, date or time formats, for example, vocabulary management, tokenization, stop word removal, lemmatization, stemming, etc. Handling data imbalance. Within certain categories, having fewer example, oversampling and undersampling, it can address the issue by balancing the data distribution. Okay, that makes sense. And then encoding and vectorization data, where we really want to switch basically things to numbers so that we can process them. And which algorithm we use gives us different kinds of vectors with different kinds of values, right? Like the bag of words, just a count, where like TF-IDF, it gives us like decimals, you know, what those mean. And then ultimately, we can take that vocabulary complexity and work with it numerically. All right, that I think covers all the content here, folks. And they have some reflection questions here if you wish to challenge yourself with them. I will be putting the homework together, and I am, and I'm just not afraid to admit this here, that I'm not really liking what Intel gave me as an assignment suggestion, so I'm going to be tweaking it pretty heavily. It will not be coding this time around. That'll come later. There is a part 2 to this data pre-processing thing, and we're going to be covering that next week. So this content ends here, and this video ends here.